Hello and welcome to the last video on forces and friction, chapter 5.3 of the second year of the A-level mechanics course. So we've looked at friction in the previous chapter. We're going to extend that idea into what happens when friction hits a maximum point and can go no further, and indeed is there a way how we can calculate the magnitude of the maximum friction for any particular surface and object combination. So before we get going with this, I've got 3 warm-up questions for you to have a look at. So here they are now. So press pause on the video and have a go at these now, and then when you're ready to see how you've done, press play to see the answers to them and self-assess to see if you've got them right or not. Okay then, so let's get going and have a look at warm-up question 1. So we've got 4 different force systems here, A, B, C and D, and acting on a given mass, which is 2 kilograms in each time. We just need to place a tick on the diagram or diagrams which show the block in equilibrium. So in equilibrium just means where the forces are perfectly balanced. So if we look at A, upwards 2G and 2G they balance, but 7 and 8 don't. So A is not in equilibrium. B, 2G and 2G balance, as does 8 to the left and 8 to the right. So actually B is in equilibrium, so we can tick B. Are there any others? Well, C isn't, because 8 is different to 6. And nor is D. G doesn't balance with 2G, even though 8 does balance with 8. So this one would be accelerating downwards. So D's not in equilibrium either. The only one that is system B. So that's the only one we need to tick for question 1. Question 2, it says, of those in question 1 not in equilibrium, we need to find the magnitude and direction of the acceleration. So we need to state the direction of this acceleration as well, whether it be up, down, left or right. So reminding ourselves from question 1 of those systems, there were these 3 here. A, C and D weren't in equilibrium. So I'm just going to section this off here, then we can work out the magnitudes of the resultants on each and therefore the accelerations of each. So for A, there's going to be no net force up and down. There's only going to be a net force horizontally. And so if we just consider the horizontal forces, just going left and right, then there's 8 going to the right, and 7 going to the left. So overall we're going to have 8 minus 7, which is 1 newtons to the right. We can now apply F equals ma. The resultant force is 1 newton to the right, and that's going to equal the mass, which is 2 multiplied by the acceleration. If you now divide both sides by 2, therefore the acceleration is 1 divided by 2, which is 0.5 meters per second squared, going to the right. So that's it for 2A. Whoops, wrong arrow type. I mean to do this. There we go. For C, there's no acceleration up or down because 2G balances with 2G. So again, we can just consider going horizontally. That's not quite horizontal, which will annoy me and no doubt maybe some of you. So this time, 8 minus 6 is 2. So that means we've got a 2 Newton force acting to the left as a resultant. And again, we can now apply F equals ma. So therefore, a resultant force, which is 2 newtons, that'll equal the mass of the object, which is 2. So just to highlight where this m is coming from, the mass each time is 2 kilograms. So that's why I'm saying that's 2. And the resultant force each time is just what I'm getting here. So just to go back for a moment, resultant force is 2. And the acceleration is what we're wanting to find. So 2 equals 2 lots of acceleration, divide through by 2, therefore the acceleration is exactly 1 meter per second squared. Only this time, because the resultant's acting to the left, the acceleration will also be acting to the left. Finally, system D. There's no horizontal acceleration because 8 to the left balances with 8 to the right. However, going up and down, we can see that there will be an acceleration downwards. And so if we just consider the up and down direction, the vertical direction, 2g down minus g up equals a force of g newtons acting downwards. Now you've probably guessed it, and we can apply F equals ma once again. Therefore, resultant force this time is g. So g equals mass, which is 2 multiplied by the acceleration. And again, just highlighting that the mass is 2. So therefore, the acceleration acting downwards, A, is g over 2. G is 9.8, so half of 9.8 gives us 4.9 meters per second squared acting down. And that's all we need to do for question 2. Finally, question 3. We have a block of 2 kilograms mass. We're told it's sliding down a smooth plane inclined at 30 degrees to the horizontal. With the space provided, we need to draw a force diagram to show the forces acting on this block. So let's get started. So if you're sketching a diagram, do it nice, big and clear, as big as the space in the exam will allow, to be fair. So next I'm going to draw the block. I'm just going to do this as a particle. So there we go, that's my block. Doesn't matter too much if it looks like a particle, that's okay. Now it's got a mass of 2 kilograms. Okay, so if we want to, in fact I think I do, I can label on that the mass is 2 kilograms. Like so. Because its mass is 2 kilograms, that means its weight, which will be acting downwards, will be 2g. That'll be 2g. And as well, we're told that it's inclined at 30 degrees to the horizontal. So we can say that's 30 degrees. And that's based off the fact what we're told in this question. So now we can use what we talked about in the previous lesson video, how we can resolve the weight going perpendicular and parallel to this slope. So if we do this, we can say that going perpendicular to the slope is a force like this, and then going parallel to the slope is a force like this, a component, I should say. This is a right angle. What I talked about last time is that this angle here will always be the same as this angle that the slope is inclined at, so that's going to be 30 degrees as well. Again, what we mentioned in previous sections is that the component opposite to this angle we know will be the hypotenuse, 2g, multiplied by sine of the angle. Whereas the component going adjacent to the angle we know will be the hypotenuse, 2g, cos of the angle we know. Now, this plane is smooth, so there's going to be no friction resisting it. However, there will be a normal reaction force. The normal reaction force is always perpendicular to the plane. So this normal reaction force here, we can label on resolving forces perpendicularly to the slope. We can say that this n must be balancing perfectly with this 2g cos 30. We can now choose to resolve forces going parallel to the slope. And so if we just consider now for part B, we've done part A. So part B, forces going parallel to the slope and using F equals ma. So going down the slope is 2g sine 30 and nothing else. So the resultant force parallel to the slope going downwards is just 2g sine 30. And that component of the weight will be equal to the mass of the object, which is 2, multiplied by the acceleration. So therefore, dividing both sides by 2, or what we could do is just cancel off the 2 on both sides, A is just simply g multiplied by sine 30. So g, for physics, for some reason, they'll give it to 9.81 for A-level, but mathematicians, for A-level, g is 9.8. So 9.8 sine 30. Sine of 30 is one of these exact trig ratios, but I can forgive you this once for not remembering. The fact this comes to an exact value of 4.9. So it's 4.9 meters per second squared down the slope. Pardon me. Now hopefully we're fully warmed up. So let's have a look at the main part of this lesson, talking about maximum friction. So I've titled this bit, half joking, friction the clever force. And I think it is, for a brainless concept, it's quite a clever thing. So I'm going to explain what I mean. So what is friction? Well, it's a force which opposes motion between two rough surfaces. If just one surface was smooth, it wouldn't interconnect or lock with the other, and there'd be no friction. So between the interface of two surfaces, there has to be a certain roughness where one surface interlocks at the microscopic level with the other, which causes a bind, which then takes energy to undo. Anyway, it occurs when two surfaces are moving relative to one another, or when there's a tendency for them to move relative to one another. So it's when one object is having a force applied to it and is almost on the move, but then is being resisted, and this resistive force is the friction. So here's an object. This here is a diagram of a book. Acting downwards is its weight, mg. Acting up is the normal reaction force provided from this surface upon the book. So like I'm saying, this book of mass m is stationary. There's no horizontal force being applied, so there's no tendency for this book to move. Hence, there's no frictional force acting on the book whatsoever. The only forces acting on the book, as you can see, are its weight, mg, and the normal reaction force from the surface, which is r. Let's think of something else now. Let's imagine now somebody on the right trying to pull the book along the surface with a small force. Let's call it P. P standing for a pulling force. The force P will result in the book having a tendency to move in the direction of P. But as long as P is sufficiently small in magnitude, it will be resisted by a force of friction, F, acting opposite to P, like this. So P, a small force trying to pull the book along, as long as P is small enough, the friction will be able to resist that and cancel off this pulling force, so F and P will be balanced, R and mg will still be balanced, so here this book would still be stationary. So the point here is, and why I've called it the clever force, the clever thing about the frictional force is that up to a certain point at least, F will and can exactly nullify the pushing force P and is able to change its value accordingly. If P is very tiny, F will be exactly that tiny in the opposite direction. If P gets a bit greater, F will be that bit greater too to counteract P. So what we're saying here is, so long as P is relatively small, F will always be equal and opposite to P, thus there will still be no motion. But what if P grows and grows up to a certain point where the friction can no longer stop it? So imagine that the pushing force P increases to a point such that F can increase no further. I've put in brackets here. Remember, friction never has an infinite limit. It's always going to have a limiting value. So when the friction becomes its maximum value, we can call this F max, which just means maximum friction. As the magnitude of P increases beyond the maximum value of the friction, there will then be a resultant horizontal force that means the book will then move to the right-hand side. However, the friction doesn't disappear and it will still be modelled to be the maximum friction until the book stops moving. And so the friction will max out at a certain value and will stick at that maximum value so long as the object in question is in motion. So I'll have this scenario here. So P now is pulling the book along, the friction still exists and is at its maximum value, resisting the motion, but there's still a net force acting horizontally, so there's still a net acceleration in this direction. And once again, mg and r are balanced, so there's no vertical acceleration. So, just let's use some intuition now, some sort of educated guesswork. It's fair to say that the heavier an object is, the harder it is to pull or indeed push. So let's imagine the weight of one book was 10 newtons, say, so about 1 kilogram. And let's imagine the maximum frictional force for the book on the surface, for example the table, let's say that's 2 newtons. So how might the maximum friction change if we actually had a stack of 3 identical books, one on top of the other? So using your intuition and having an educated guess, I want you to fill in and complete the boxes below. So this is a situation from before. So the weight, 10 newtons, normal reaction 10 newtons. F max, we've said, is 2 newtons, and if it's moving along to the right, then this pushing force will have to be at least 2 newtons. So here I'm just saying it's greater than 2 newtons. Don't know what it is, but as long as it's greater than 2 newtons, it will move to the right. So based off that, what might the situation look like if we had 3 books? So this is what I want you to have a good guess at filling in. So freeze the video now if you want to, or just watch and sort of follow my logic as best as I try to explain it. So if we have 3 books, then the weight will be 3 times 10. So it'll be 30 newtons acting down. Therefore the normal reaction acting up will be 30 newtons to counteract that. Now, like I say here, the heavier the object, the harder it is to pull along. So here, this stack of 3 books will be 3 times heavier than just 1 book. So I'm hoping you might have guessed or thought that, therefore, because it's 3 times heavier, it'll be 3 times harder to push or pull, and that's because the friction will be 3 times greater. So here F max will be 2 multiplied by 3, which would be 6 newtons. And that means that this pulling force would have to be greater than this F max now of 6 newtons. So the point I'm trying to drive home here is this intuitive idea, in my opinion, that the friction maximum, the maximum value of friction is proportional to either the weight or the normal reaction force. Now it turns out that it's proportional to the normal reaction. So to summarise, intuitively, if the load is tripled, it'll be harder to move by a factor of 3. And that's because the normal reaction force increases by a factor of 3. So what is actually the case is that for any surface, the maximum friction is proportional to the normal reaction R. Going back to GCSE and direct proportion, we can now say that the maximum friction is proportional to R, therefore the maximum friction equals some constant multiplied by R. And this constant of proportionality K actually has a special name. The constant of proportionality K changes dependent on the surfaces in question, so it's higher for rough surfaces, for example. In general, for any surface, we have that this constant of proportionality K is actually called mu. So it looks like a U with an elongated tail. So F max equals mu R, where mu, this factor, is known as the coefficient of friction for the surface-object interface. So the higher the value of mu, the greater the value of the maximum friction. The lower this value of mu, the smoother the interaction between the surface and object in question. Let's have a look at some examples using this concept of maximum or limiting friction. So first off, worked example 1. We have a particle of mass 5 kilograms being pulled along a rough horizontal surface by a horizontal force of magnitude 20 newtons. So let's add in to a diagram as we go along. So horizontal surface, so a straight line across. It's a particle of mass 5 kilograms, so I'm just going to sketch in a particle. I'm going to make it spherical. Get this coloured in black, why not? That's 5 kilograms. So I'll label in that it's 5. Because its mass is 5, we can also, and therefore also should, add in its weight. So its weight will be 5g. And the normal reaction force will be equal and opposite, therefore will be 5g acting upwards. And we know this because this pulling force is acting horizontally. So this horizontal force of magnitude 20 newtons, we can just add in like so and label that 20. Or 20 newtons if you want to add in the units. The coefficient of friction between the particle and the floor is 0.2. So now we need to recall that Fmax equals mu r. Now, because it's being pulled along, because it's moving, this object must be moving to the right by this pulling force, and so we can add in here that the direction of motion must be this way. So therefore, if the object's moving, we know that this frictional force must be Fmax. It must be at its maximum possible value. So I'm going to label this here Fmax. So for part A, the magnitude of this frictional force, we can say it's Fmax, which is mu r. Now we're actually told what mu is. We're told that the coefficient of friction between the particle and the floor is 0.2. So mu is 0.2. Now this normal reaction force, again we've worked out, must be equal and opposite to the weight. So that's going to be 5g. So Fmax is 0.2 multiplied by 5g. 0.2 times 5 gives us g. And that, therefore, is going to be 9.8 newtons. And part B, the acceleration of the particle. We need to just work out the resultant force. So we can now apply F equals ma. And think about this going horizontally only. So in the horizontal direction, we've got a force of 20 going to the right. Going to the left, we have Fmax, which is 9.8. 20 take 9.8 is 10.2 newtons acting to the right-hand side. So that's the resultant force. So the resultant force acting to the right is 10.2 newtons. And that'll equal the mass of the object. So mass is 5 multiplied by the acceleration. I apologise, I've got a slight cold going on, but I'm doing my best. So therefore, the acceleration is going to be 10.2 divided by 5. Use your calculator if you want to, that's absolutely fine. 10.2 divided by 5. That gives us, to 3 sig figs, 2.04. So the acceleration is going to be 2.04 meters per second squared to the right, or the positive x direction, you could have also maybe said. So that's worked example 1 done. Let's have a look now at worked example 2. So we have a block of mass 5 kilograms, and again it's on rough horizontal ground. So let's sketch in the horizontal ground of the block. Here's one I did earlier. And we're told it's 5 kilograms, so I'm going to label that on as well. And we're also told about this coefficient of friction. So the coefficient of friction between the block and the ground is 0.4. So we'll return to this in a moment. We're also told now that a horizontal force P is applied to the block. So horizontal just means acting directly to the left or right. I'm going to take the positive direction to be to the right. So I'm going to label this one here P. Now it says about a frictional force. So the frictional force will resist this force P. So the frictional force, whatever it might be, will be acting in the opposite direction, like so. So I'm going to label this just F at the moment. Now because the only forces being applied, which don't relate to the weight, are horizontal, P and F, we now know that there's no vertical components to these. So the weight going down will just be obviously 5g. And also the normal reaction will be equal and opposite to the weight, which will be 5g. And we know that because there's no vertical component to P and F, either pushing it up or downwards into this surface. So the normal reaction R must be 5g. We can now return to this idea about this coefficient of friction, because we know what F max is, because it relates to the coefficient of friction, mu, and the normal reaction. And we now know both of these. So we know that mu is 0.4, and we can also see by thinking about this force diagram that the normal reaction has to be 5g. So 0.4 multiplied by R, which is 5g, that gives us 2g, and 2g, g in ALevelmaths is 9.8, so 2 lots of 9.8. Let's see what that gives us. That's going to be equal to 19.6 newtons. So we can return to this later on if we need for parts A, B and C, because for A, B and C we need to find the magnitude of a frictional force acting on the block and its acceleration, when P is, first of all, 10 newtons. So when P is 10 newtons, F will always try to resist P. Now because the maximum friction is 19.6, 10 is within the realm of possibility for the friction to be. That's only about half of its maximum value, so the friction is able to resist this force of 10 newtons. So the frictional force will be equal and opposite. It'll be 10 newtons as well. So therefore there will be no acceleration. The object will be in equilibrium still. For B, when P is 19.6, well, 19.6 is actually the maximum possible friction. So F will be at its absolute maximum, which will be 19.6. So it'll be on the verge of moving, will this block. So there'll be no acceleration. And this will be a limiting case. So it's on the limit of being able to accelerate and move. If this pushing force, P, gets any greater, the friction will not be able to stop it, and there will be a resultant force, therefore a movement and an acceleration. So C, when P is 30 newtons, pardon, the resultant force going horizontally that's going to be P, which is 30, minus F, which will be F max, which will be 19.6. 30 take 19.6. That's going to give us 10.4 newtons. We can now apply this idea of F equals ma in the horizontal direction. So the resultant force, which is 10.4, equals a mass of the object. Well, we worked out the mass earlier. The mass is 5. Sorry, we didn't work out the mass. We were told what the mass was. Apologies. So 10.4 equals 5 multiplied by the acceleration. Therefore, the acceleration of this block now will be 10.4 divided by 5. Calculator if you wish. So 10.4 over 5 gives us 2.08 meters per second squared. And give a direction, it's going to be to the right. And I've got one final worked example before I suggest you try some questions yourselves. So the final worked example is here. So this time I've got a particle of mass 2 kilograms which is sliding down a rough horizontal slope that's inclined at 30 degrees to the horizontal. So let's fill this in as we go. So a slope, it's 30 degrees to the horizontal. And this object's going down, it's got a mass of 2 kilograms. So a nice big clear diagram as ever if we can. So I'm going to draw in this particle. Let's do it as a big black blob. There we go. Now it's 2 kilograms, so I'll label this in. Now the slope's 30 degrees to the horizontal, so that's going to be a 30-degree angle, like so. And because its mass is 2 kilograms, we can therefore clearly and obviously hopefully say that the weight is 2g, acting downwards. However now, based on the previous lesson, we can resolve this weight into components going perpendicular to the slope and also down the slope. So let's do this now. So perpendicular to the slope is this direction, and then parallel to the slope is going to be like this. We should also be comfortable with this idea now that if the inclination of the slope is 30, then this angle here must also be 30 degrees as well. We also need to remember the component of the force acting opposite to an angle will be the hypotenuse of this force triangle, which is 2g, because it's opposite to this right angle here, of course. So the hypotenuse multiplied by sine of the angle. So the component going parallel to the slope is 2g sine 30, whereas the component which is adjacent to this angle is the hypotenuse 2g multiplied by the cosine of the angle. So that's cos 30. There's still a bit more labelling to add on as well. We have been told in this case that the acceleration of a particle is 1 meters per second and that it's going down the slope. So we can infer from this that the acceleration is going down the slope like so. So a double-headed arrow to say that this is 1 meter per second squared. Investing the time with a carefully labelled diagram is never ever a waste of time, so never be thinking this seems like too much of a hard effort, I'm going to ignore doing this. Don't. Always do a carefully labelled diagram in mechanics, unless a question is absolutely trivial. So we're not quite finished yet. It's a rough slope. Rough implies there's going to be friction. Now because it's sliding down, there is motion Therefore, we can deduce, because there's motion, the friction will be F max. It will be the maximum friction possible. So acting back up the slope, we can label in this frictional force. So I need to choose a different colour. Let's go for purple. So that's going to be F max. Now what's that going to equal? Well, we might be able to work this out. In fact, we can. So this particle's acceleration will be parallel to the slope, which means there's no acceleration perpendicular to the slope. We've not labelled in yet the normal reaction force, so let's do this right now. So the normal reaction, R, because there's no acceleration perpendicular to the slope, this particle is not flying off and up, nor is it going to be falling into the slope and burying itself. This reaction must be equal and opposite to this component here, which is 2g cos 30, to keep it in balance. So R must as well be 2g cos 30. Now F max equals mu multiplied by R. Now in this case, we don't know what mu is, that's what we're trying to find, but we do know what R is, because R is 2g cos 30. So that's going to be 2 mu g cosine 30. So that's as fully labelled as we can do, really. That's a very inclusive diagram. So we need to work out the coefficient of friction. We know it's a particle, we're told its acceleration, we know its mass. We can work out the resultant force parallel to the direction of motion. So this is a very dressed up question which just relates to F equals ma. So let's apply F equals ma going parallel to this slope. I'm going to say that going down the slope is positive. So taking down the slope as positive. Try and do my line better. No, third time lucky. There we have it. So I'm going to say that down the slope is positive. So the net force, resultant force going down the slope, is going to be 2g sine 30, because that's going down the slope. Subtract the forces acting against this direction. So a force acting up the slope is the friction, which is resisting the motion down the slope. So that's going to be 2 mu g cos 30. So 2 mu g cos 30. And that's going to be equal to the mass of the object, which we were told is 2, multiplied by the acceleration, which again we were told is 1 meter per second. So that's 2 times 1. So next up we can rearrange. So if we add 2 mu g cos 30 to both sides, we get that 2g sine 30 equals 2 mu g cos 30, and obviously 2 times 1 is 2. Subtract 2 from both sides now. 2g sine 30 subtract 2 equals 2 mu g cos 30. Now we want to have mu on its own, so what we can do in this scenario is divide both sides of this equation by 2 by the g and the cos 30. If we do that, we can work out what mu is. So therefore mu, the coefficient of friction, will be 2g sine 30 minus 2, all of that divided by 2g cos 30. So let's see what the calculator tells us. So 2 times g, which is 9.8, multiplied by sine 30, close a bracket, very important, minus 2, all over 2 times 9.8 times cosine of 30. Close brackets, press equals. We get this awkward surd. Press S arrow D to get it to a decimal. We can see here that it's 0.4595, so to 3 significant figures, that's going to give us approximately 0.460. So a slightly trickier worked example there, but there we have it. Sometimes these questions will be hard. So how do we get good at these questions? It's by doing more and more of them until you can't stomach doing any more. On that note, over to you lot. So if you turn to page 103, exercise 5C, these are my suggestions for what you might want to try to get very good and fluent at these types of questions. So try question 1, A, C, E, J, K and L, then questions 2 through to question 7. If you're able to stomach more questions, absolutely great, be my guest. So thank you again for listening and tuning in. Please do subscribe, and I'll see you all in class or in the comment section perhaps very soon. So, as once again, goodbye for now.